So I'd like to invite up next speaker, Jordan Fisher. So she is a lead AI developer and solutions architect at IBM's Public Services division. So she designs and integrates AI solutions for the U.S. government, working on large language models, foundation models on things like AI governance, responsible AI, and adversarial AI robustness. So she's going to talk to us about some tools to evaluate and harden AI models. So,
hi everyone. Thank you for the introduction. So I will share with you guys today a couple tools that I at IBM Consulting and colleagues at IBM Research have been working on to provide testing and evaluation tools for AI models. The tools are called ART and HART. How do we go to the next slide? One moment. There we go. Okay, thank you. Okay, so I'll start with ART. That is Adversarial Robustness Toolbox. ART has been in existence in the open source world for about a decade now. It started with IBM Research. It's now hosted by the Linux Foundation. And ART provides a really wide range of tools that help AI model owners assess their model's performance under adversarial attack. And then should that performance be suboptimal, it also provides tools that help improve models' resiliency in the case of this kind of attack. And in the last couple of years, in collaboration with the CDAO's JTIC program, that's Joint AI Testing Infrastructure Capability, IBM has created a hardened extension of ART, or HART, which is a curated subset of those tools with an emphasis on DoD needs and use cases. So that's going to be, a focus on computer vision models, a focus on evasion attacks, which I'll get to in a second. And it also provides an alignment to best-in-class standards, including protocols like the MAPE protocols, to facilitate testing in environments with stringent criteria. So these are both open source Python libraries under the MIT license. They include things like step-by-step tutorials. In particular, HART has built out in-depth documentation, explanations, support materials, reference materials for ease of use and ease of adoption. And they both support red and blue teaming, which I will explain later. It's a framework for adversarial T&E. Many of you guys are probably already familiar with adversarial threats to AI, but just to make sure we're all on the same page, I'll go through quickly some base concepts. So adversarial threats to machine learning and AI come into four sort of categories. We have evasion. That's when an attacker modifies the data that the model runs on at runtime. And that's the focus of the HART library, sort of DoD uses. But we also have poisoning, which will be coming soon to the HART library, in which the attacker modifies the data that the model is going to be trained on, which can add sort of a backdoor that the attacker can use to their benefit at runtime. There's also extraction, where an attacker can probe a model to steal proprietary information, intellectual property about the architecture, the way the model is set up. And then there are inference attacks, in which a similar kind of probing can be used to sort of reverse engineer the data that the model was trained on, which can be obviously problematic if it was trained on sensitive data that the owners of the model don't want out into the world. And these types of attack can be used together. For example, an extraction attack can be used to better inform a white box evasion attack. Different combinations, you can build them off of each other and make stronger and stronger attacks to models. Quick vocabulary check. A black box attack is an attack in which nothing is known by the attacker about the model's architecture or parameters. And a white box attack is one in which the attacker does have familiarity with the model's architecture and parameters. Typically, white box attacks are harder to defend against, but also still possible to defend against. So I'll take you guys through some examples. This red and blue teaming approach that I mentioned earlier, which is sort of the framework that Art and Heart both support. This is an exercise in which the model's sort of support team or owning team splits into two. Half of you act as the model owners and half of you act as the adversaries who are attacking the model. So the blue team, which is the owners, make a model. It works perfectly in a lab setting, but then the red team comes in and will attack the model. The blue team will arm some kind of defense. The red team attacks more strongly, with greater attack strength, and so on. It's like an arms race. So in order to so in this red-blue teaming approach within the Heart package, Heart has as I mentioned, a focus on evasion attacks. So the attacks that are currently supported by Heart, we're adding more all the time, but we have projected gradient descent, PGD. This is in many cases a worst case scenario. It's a white box attack. So the attacker understands the architecture of your model, has the parameters, and is able to calibrate just the most efficient attack that is least noticeable but most harmful, right? We also have patch attacks. So these are interesting. They can kind of fit any category. They can be white or black box. They can be realized digitally or physically. And Heart supports all that range. We have hop, skip, jump attack. So this is a black box attack. So even if the attacker doesn't know anything about your model, this attack can be used to sort of probe and discover model thresholds that can then be used that can be exploited. And finally, we have a laser beam attack. It's a little bit of a low-hanging fruit attack, but most models out there in the world are not prepared for it. It's actually just shining a laser at the object that you don't want the model to identify or classify. So it is pretty easy to perform, but it is also quite effective in an alarming range of scenarios. So we also support this kind of attack as well. Heart also has defenses or mitigating defenses. So all the way from sort of more quicker to deploy pre-processing and post-processing steps like spatial smoothing or image compression. And then there's adversarial training. So in the example of the laser, if you want your model to recognize that an object with like a light beam on it is still the same object, you can train it on images with light beams on them, right? So that's the most straightforward example of adversarial training, where you're going to incorporate the adversarial examples into your training data to make the model more resilient to them. We also have detector defense. This is a framework where it aims to identify adversarial images, adversarial inputs, in order to discard them from model results. And then transformer defense, which is underway, coming to Heart soon. But this is even more involved, where we are training a deep learning model to smooth decision boundaries and improve robustness. So this is the range of things supported by Heart. Art has a wider range of attacks and defenses that are supported, but they are sometimes less applicable to the DoD and a little less supported by, as I say, they're not necessarily complying to all these protocols and things like that. But the two packages work together and can, both can be useful depending on the need. Just a couple additional sort of concept checks, and then I'll take you guys through an example, and then we can get to questions. So there's an important concept of perturbation. So this is basically the difference. This is the change that the adversary makes to the input data to cause a detrimental result, right? So the difference between your unmanipulated benign image and your manipulated adversarial image is just perturbation. In the case of a projected gradient descent or PGD attack, this is this pixel by pixel, really carefully calibrated changes that are overlaying over the base image. And as you can see in the image labeled adversarial example, it doesn't look different to the naked eye. This is the PGD attacks are very difficult to detect and therefore can sort of achieve maximum damage. When we look at evaluating how a model is doing before and after attack, as I mentioned, we have this focus on computer vision models. So we're looking at image classification and object detection. For image classification, we use accuracy, number correct out of total number. And for object detection, we use mean average precision. This is MAP. It's the difference between the ground truth object detection boxes and the predicted object detection boxes that the model produces. Before attack, we're looking at clean or benign metrics, and after the attack, we're looking at, there are two ways to calculate robust or adversarial metrics. They're pretty similar. Adversarial accuracy or MAP just throws out the examples that were not correctly identified or classified even before attack. Whereas robust accuracy or MAP take the whole thing into consideration. So I'll take you guys through a red-blue teaming example using PGD, our favorite, most effective attack. So we start with the blue team, right? The blue team has a model using HART. They pull the model in. Here we're just using easy to grab YOLO v5 object detector, but in context, the user would want to pull in whatever model they're working with all its sort of like presets and surrounding processing. So the blue team has this object detector, runs it in the perfect lab setting. It performs pretty well. We have a high accuracy, a decent MAP, and you can see with the bounding boxes, and I don't know if you guys can read the labels, but it's doing pretty well. It found the people in the bottom right-hand corner. It's mostly identifying cars correctly and things like that. But then we have the red team come in and runs a PGD attack against this object detector. So that means that they are manipulating the images that are going into the object detector to decrease its performance, right? And you can see it's been very effective because this model is completely undefended. So our classification accuracy plummets, our MAP is abysmal, and you can see that in the labels. We're finding a van in the middle of the street where there is none. The people in the bottom right-hand corner are completely undetected. And we found a bunch of cars in the trees on the top left. So the model is not doing well. This attack has been very effective. So one of the quickest defenses that the blue team can mount is going to be one of these mitigating defenses that is pre-processing or post-processing changes to the images that can minimize the damage done by the manipulation that the red team put in there. So mitigating defenses aren't going to give you 100% protection against any kind of attack, but they're going to really decrease the damage that the attack can do. So in this case, we apply a spatial smoothing pre-processing right before running the model. So that means that those carefully calculated perturbations that we saw, those little pixel changes, when you compress the image or you smooth the image, at a pixel level, those changes kind of average out. So the impact is not as strong. And you can see with the mitigated image on the right-hand side of the slide, we're no longer hallucinating cars where there aren't any. We found one of the two people in the bottom right-hand. So, progress, we're having an improved result. And we're no longer hallucinating that van. However, it's not perfect. We still have, if you can see the yellow circle, we are still finding a pedestrian where we weren't finding them before. But in comparison to the unprotected, undefended adversarial image, we were previously finding like 15 people in that corner, and now we're only finding one. So you can see, reflective of that, classification accuracy is almost back to as good as it was, and MAP is also significantly improved. Of course, the adversarial team, the red team, is going to come back and, mount an even stronger attack on the defended model. And that stronger attack is going to be, a little bit better. And it's just going to go on like this as an arms race. So these tools, this technique, this framework of red and blue teaming, it allows model owners to test in a relatively controlled environment this kind of attack and ensure that their models are as robust against them before putting them out into a real world context, into a production context where they are vulnerable to true adversarial attacks. So whenever we talk about tools in the defense and intelligence space, we want to talk about ATO and access. So just a couple points on that. I mentioned earlier, ART and HART are both 100% open source Python libraries under the MIT license. ART and HART are both available in the JWIC's PyPy repository. That's the Joint Worldwide Intelligence Communication System. The HART and other JTIC packages are also available under the on the Advana platform. I mentioned HART is part of the JTIC program. There are also other tools for testing and evaluation available through that program. And this just allows them to be even, have a higher degree of readiness for DoD applications. We also work actively with stakeholders and potential adopters of these tools to help these packages into ATO'd environments without affecting the existing ATO status, be that through files, scans, containers, and in general, HART is built to be as backward compatible as possible to minimize the need for updates in already approved environments. So these tools exist and they are in use, but we are, of course, looking for wider adoption. The CDAO already paid for them. We just want to get them out there. So I'll share with you guys a couple QR code links. On the left-hand side, we have the tools, ART and HART. These are open source GitHub repos. In the middle, we have the JTIC, CDAO JTIC program, which is going to have both HART and other tools for testing and evaluation for the DoD context. And of course, if you have any questions, myself or other members of my team will be happy to answer or connect you to other members of the team who may be able to better answer your questions. I think that's all I have. I think we're decent on time. Thank you guys for saving your questions to the end. Does anybody have any questions, comments?
A quick clarification question about the red teaming and blue teaming. If we just go back to those slides over here. So go forward.
Oh, I was going to go to the very original one.
So yeah, right. So here, when the blue team had the model trained and the red team came back and supplied you with the perturbed image, is the process then retraining that model, or are you just smoothing the input image to have a better classification?
The case I'm showing you, as I mentioned, these are mitigating defenses, so this is a pre-processing step. So the model doesn't need to be retrained for this step, for this type of defense to improve the outcome. However, potentially, so then the attacker comes back and they mount another attack which is stronger, so then the blue team may turn to a retraining option. This is what I mentioned at the beginning. One of the defenses is going to be adversarial training. So that's when you incorporate adversarial images into your model. It teaches the model to to calibrate its weights and parameters a little bit more in a way that will provide more resiliency. So this example specifically is a mitigation, but adversarial training is definitely a valid option.
Just to clarify, how much is your red team, blue team human interface? Is there a man in the loop, or is it all machine that's doing the red team, blue team? And the second question is, have you experimented this with warfighters?
So it is definitely human in the loop because the goal is sort of calibrating how we want to do this kind of, we want the human decision because it's decision making on how the model can be most improved. There could be suggestions of what is going to be a good, route to go in terms of defending or attacking, but the decision is made by a human. And then the second question was, have we used it with warfighters? So we have worked with DoD teams. I guess, forgive me, I am civilian. The term warfighter, I'm not sure. Military, yes. So I don't know if it's not necessarily active combat context, but definitely with the military, we have examples, teams who are using it.
I tend to imagine this being kind of used the most in earlier kind of model testing with
Exactly.
ML experts. Do you also, I could also see this being useful kind of either with ML experts in conjunction with cyber teams or making user interfaces kind of toolboxes integrate with some of the cyber tool sets. Have you thought about doing some of that to pull it into some of the later testing at all, or any thoughts on where this might go in the future?
Yeah, so as you say, it is generally designed for, so there are two sort of types of users that we aim to provide tools for. One is going to be your model builders. So as I build a model, I want to set it up initially to be relatively robust. But then someone who is unfamiliar with the model, we also have tools for T&E specialists, right? So these are both still relatively specialized. And I may be biased, right? Because I'm on the model building side. So that's the most common in my experience. But we definitely have tools for T&E specialists who maybe had nothing to do with building the model, but are just testing the model as part of its sort of like standard testing.
Do you view this more as like a mitigation for potential cyber actions in the future, or is it like aimed towards denial and deception that may lead to sort of lower fidelity data coming in when the model's applied to it? Like, what's the vision here?
So it is it's a toolbox, right? So there are tools that you can use in different ways. We definitely have this sort of prepare your model for deployment sort of use case, but it can also be, if a model is out there and has, in a, use production sort of situation, and the model receives an attack, the defenses can be used even if you're not the one simulating the attack, right? If there's actually an attack, you can still use these tools for the defensive side. So it's kind of how you use it, I think.
You mentioned two physical attacks, the laser beam and the patch attack. I'm assuming that this tool is supporting simulation of those physical attacks and not realization, like validation out there. Is that correct?
It depends on, so these tools are, you can use them with your own models and your own data. They're designed to be used with your own models and your own data. We have examples that use easily accessible, like Hugging Face data sets or things like that. But to really get, good use of the tools, you should use your own data. So if you have for your models examples of physically realized attacks that you have those images to use, that's optimal. That's an optimal use of the tool. We don't. So this is a tool that tests models and their data and evaluates their performance and helps improve them. It is not a model itself. So whatever you have for your model and your data, that is useful to the tool. So if you have physically realized attacks, coming back to this sort of like, oh, we actually did get attacked and now we want to defend scenario, you can input that and the tools will be helpful in overcoming that.
So if you, for example, if you ran the patch attack and you found that a patch that was successful against your model, that's still a digital representation of the patch. And so in order to validate that in the real world, you would have to actually create that patch out in the real world and then run it on a real system.
If you wanted to test the physical viability of a patch, because patches could be digital, you can overlay them digitally over images, or they can be physical, like you put a sticker on a sign, right? So if you wanted to evaluate in a testing context, does this sticker patch work? You would have to go put a sticker on the object you're identifying and take a photo of it, yes.
So I guess I was just wondering if you have any support for creating that physical validation,
like designing a patch and then, designing a patch to be printed, yes. But you would have to do the printing. Yeah.
I apologize to the previous speaker. I didn't know we were supposed to hold our questions. I know now.
It was, we had different, I requested for them to be held. He did not.
This is a video, right? So this is constantly changing, right?
Mhm.
This is not, this is a, like in the real world, if you're running this model, you do this
Right.
picture is constantly up. The people are moving, the cars are
Mhm,
moving.
mhm.
Someone asked a really dumb question. So spatial smoothing, if as you start to degrade in your models, right, as you're being reattacked, can you focus your spatial whatever smoothing to an area of higher prioritized interest? Like as you're slowly starting to grade this picture,
Mm.
can you increase the accuracy in a certain area? Like, is it a resourcing issue or is spatial smoothing just across everything?
It's a pre-processing technique applied to the entire image. I would say if you only care about one area of the image, I would crop the image accordingly.
Okay.
Rather than trying to apply different pre-processing to different areas of it.
I'm just thinking of more like a cyber mindset where we're trying to fight through the problem, right? We have to apply more resources to a smaller area to keep that critical thing going.
Yeah.
That's even analogous in this situation. Probably not.
Yeah, I would just, if you're worried about a specific part of the image, I would just lose the rest of the image, would be my recommendation. Yeah.
You mentioned that there's gradient descent attack required. So you just couldn't give random noise for that interpret.
Correct.
So does this mean it's more of a white box attack?
Exactly. Yeah. So the predicted gradient descent is a white box attack. It's a really strong attack. It's really carefully calibrated. It's optimized. There's a lot of calculation going on back there. So that's sort of the most fun example to work with, I think, because it's sort of a extreme case example. But as I mentioned, patch attack is sort of the classic, works in every kind of way. And then, we have really easy black box like laser beam. Those are all supported. Yeah.
The name of the analogy to kind of cyber, we want to emulate adversaries and make sure we're executing TTPs that we would see in the real world. Is IBM or kind of industry writ large kind of tracking and documenting some of this so that we can kind of understand what's happening in the real world and try to implement more of that in test events?
Yeah, absolutely. So one of the advantages of having both these tools, Art and Heart, be open source is that we can accept open source contributions. So I mentioned Art has been around for about a decade, and there have been multiple contributions from members of the open source community. Any contribution is, of course, vetted before approval by our team, but it allows us to sort of pull in different newer use cases, newer scenarios, and sort of crowdsource this kind of, what's going on out there updates.
Is your team working on any adversarial tools for anything other than image classification?
Yes, so Art already has tools for things other than image classification. It is possible that non-computer vision tools may get integrated into Heart at some point, but the JTIC project mandate is to provide tools for a DoD context. Of course, I know that that's not, there are other examples of
working on adversarial tools for that you haven't for besides image classification.
So in Art, yes. In Heart, no. Do you want me to talk about those examples?
Yeah, just briefly give us an idea of
Yeah.
what other adversarial tools are either available or in works for other types of AI.
So in Art, there are tools around LLMs. That's the big type of model these days. So we have adversarial tools or adversarial robustness tools for language models. There are also tools available for sort of classic, sort of more classic machine learning, like feature-based models. I think.
Again, you're talking image stuff?
No, it doesn't have to be images. If you have oh my God, the very most classic, bank data, fraud, waste, and abuse type models, they're just features.
Okay.
It's very traditional machine learning. So we also have tools for those within the Art package. Heart is much more narrow focus. Yeah.
Are you part of the minor Slack?
Part of the MITRE Slack
Yeah.
through JTAG? Yeah. Guess I'll see you on there. I think we might be ready for our third speaker.
So please thank our speaker.